Hi everyone, I'm Thomas, and together with my partner Liam, we conducted our research project on the CFD modelling of surface roughness effects on boats and aircraft, supervised by Dr. Michael McDonald. The motivation for this project is to find a viable, accessible way to accurately predict and quantify the drag on a given rough surface using the Reynolds averaged Navier-Stokes equations, or RANS. Normal methods like direct numerical simulation, or DNS, and wind tunnels are expensive, and approximate methods such as a Moody chart can be up to 30% inaccurate. It is therefore of interest to determine if RANS is a viable, accessible way forward. We conducted simulations using four models: CN Castro's previous C20S case, their previous RM10S case, a sinusoidal roughness surface to present a more realistic roughness geometry, and finally, a 3D printed surface to further apply this research to practical scenarios. CN Castro previously investigated the use of RANS, stating that it was not accurate enough to provide satisfactory results. However, we have extended their study to a more reasonable RANS model, namely the shear stress transport model, which behaves well both in the free stream and close to the wall. Our results show that RANS consistently overestimates the flow velocity, particularly in the free stream where the DNS data is consistently higher. In the C20S case, this results in approximately 30% error. Looking at these velocity vectors, it is clear that there is a strong correlation between the two datasets. The error in our results is likely to decrease as the mesh is refined more, as seen from this mesh spacing plot. This indicates that the more the mesh is refined, the closer we get to the true solution. This is promising, as it means our turbulence model is working as intended.
To better understand the effects of drag caused by the roughness, it is of interest to define the roughness function, delta U+. The roughness function is the difference in skin friction coefficients between the smooth and rough wall flows. Looking at a Moody chart, you could compare this to the friction factor. A higher friction factor results in a higher skin friction coefficient and hence a higher roughness function. We can take 2 points on a Moody chart with the same Reynolds number and directly correlate the difference between these points to the roughness function. Since our data is directly comparing the normalized velocity, U+, we can do the same with our results. A particular surface we wanted to test was a 3D printed material. 3D printed surfaces are easy to manufacture, and the technology is constantly evolving, making the material particularly relevant and applicable, such as with low-orbit UAVs. In scenarios like these, where there is a lot of turbulent flow, it is important to fully understand the effects of drag, and in particular, its relationship with the print direction. To test this, we obtained a surface profile of a 3D printed material, which had a roughness height of around 110 micrometers. We expect that, with the print direction, the material should act similarly to shark skin riblets, which reduce drag below that of a smooth wall. Against the print direction, we expect a higher drag, as the flow is effectively bumping into each of the roughness elements along the flow direction. We can see here that these results follow our prediction, mostly acting as a smooth wall before a negative roughness function is observed in the free stream, in the case of the print direction. A negative roughness function corresponds to less drag than a smooth wall. Against the print direction, there is an unexpected increase in velocity near the free stream. At this point, delta U+ should be lower than both the smooth wall and print direction flows. This issue is likely due to a simulation error and needs to be further investigated. Our research has concluded that RANS consistently overestimates the flow velocity, resulting in an uncertainty when compared to the DNS data. This is likely due to a lack of refinement in the mesh, as seen by the mesh spacing study. Refining the mesh more should result in more accurate data, whilst remaining far less expensive than other relevant methods. This proves that RANS could provide a viable alternative to DNS and wind tunnels. Thanks for listening. If you have any further questions, feel free to contact us on the emails below.